Welcome you all once again to this class. I'm Yaragula Anthony here. So today I'm going to teach you about invertible matrices and a very important theorem based on the invertible matrices, and if at all this question comes, it comes for 3 marks in the exam. Okay. So today let us discuss about two things. One is what is actually an invertible matrix, and then what is the theorem which is based on the invertible matrix. Okay, so here invertible matrix, we see here invertible matrix. So which matrix is called as an invertible matrix? See, there are so many matrices, but not all the matrices are invertible. So in general language, if I want to talk to you, there are so many matrices, but not all the matrices will have inverse. That's what. Okay. So a matrix which will be having inverse will be called as a invertible matrix. Okay. Now what is the definition? Let us see. See, here is the definition. I want you all to look at this definition very carefully. Okay. So it is just a matter to understand what is a invertible matrix. Okay. Let us see. If A is a square matrix. So for an invertible matrix, this is very important. It should be a square matrix. That means only a square matrix will be eligible for having the invertible matrix. Okay. So if A is a square matrix of order M, so M may be a 2 cross 2 matrix or it may be a 3 cross 3 matrix. Okay. And if there exists, that's what we say here, the word there exists. As I told you, every matrices may not have the inverse. There are some matrices which will be having their inverse. That's why this word comes if there exists. Okay. If there is an inverse for A, then what is the qualification for that inverse is if there exists another square matrix. See, what was A? A was a square matrix. And if at all there is an inverse for A, that also should be a square matrix. And if that matrix is B, just let us name that as a B. Of the same order, M. So, this is another condition now. Then, such that, this is the very important condition that B should satisfy to become the inverse of A. Okay, I repeat once again. This is a very important condition for B should satisfy to become the inverse of A. What is that condition? If A into B, you know how to multiply, right? Is equal to B into A, and both are equal to an identity matrix. If this condition is satisfied, then we can call B as the inverse matrix of A. I hope you followed this definition. Okay. If this B satisfies this condition, then B can be called as the inverse of A. Okay. And the inverse of A is denoted by A raised to minus 1 or A to the power minus 1. Okay. So, if A is having the inverse, then A is called as invertible matrix. Okay. If A is having the inverse, A is called as invertible matrix. Okay. That's what we say. In that case, A is said to be invertible matrix. Okay, done. Now, this is the definition of the invertible matrix. Now, the theorem which is based on this invertible matrix, as I told you that this theorem will be asked for 3 marks. Okay. So already 2 times this question had appeared in the annual exam. So here is the question. The theorem. If A and B are invertible matrices, A is also having inverse, B is also having inverse. That is the meaning of them. Okay. If A and B are invertible matrices, if both the matrices are having the inverses of their own, they are of the same order, then, now this is the theorem, prove that A into B the whole inverse is equals to B inverse into A inverse. Okay. So this is what our main target here is. Okay, I'm going to show you how to prove that. Okay, so very simple proof. Okay, intelligent students like you all can easily understand it. Okay, so I will explain you. So look at line by line, and try to understand it. Hardly few steps will be there in the proof of this theorem. Okay, so let us begin this. So what is our target? AB the whole inverse is equal to B inverse into A inverse. Okay, done. Now I am going to start the proof of that theorem. So here the proof of this theorem. Proof. Before I start the proof, I want you all to know one important thing. See, we have already written AB is equal to BA and both must be equal to I. Done? So, B is the inverse of A. Done? So, that is why we write AB is equal to BA is equal to I. So, what I do, I will write this statement as like this. This is very important statement which will be used for our proof. A into A inverse is equal to I. Or A inverse into A is also equal to I. This is the important statement of the invertible theorem, and you need to keep that in mind. So that will be helpful for us to solve this. In general, any matrix multiplied with its inverse will be equal to I, or a inverse matrix multiplied with its matrix will be also equal to I. Okay? So this logic I am going to use in proving this theorem. Okay, now listen to me carefully. How we are going to prove it is. First thing is, when you multiply AB with its inverse, that means A when multiplied with A inverse, you should get what? I. Right? So I am multiplying AB with its inverse, so that means I should get I. Okay, statement number 1. Okay, done. Then, this is what the next step is. Multiply A inverse or pre-multiply. This is what we say. Pre-multiply. Pre-multiply A inverse on both sides. Pre-multiply A inverse on both sides. Okay? So, meaning of that is A inverse into AB the whole inverse is equal to A inverse into I. What did I do? I just multiplied A inverse here and here. That's it. I just wrote it as it is and multiplied A inverse here and here. Okay, you want to see that once again? Just let me make you write. I will write this statement as it is. See, AB into AB the whole inverse is equal to I was the statement. What I am doing now? I am multiplying A inverse here and A inverse here. That's what I wrote, pre-multiply. Okay, done. Now, this cannot be opened because it is the whole inverse, but we can open this bracket. Let us apply associative property. Okay, associative property. That means I will open a bracket for these two and I put the bracket for these two now. That means the bracket is exchanged like this. A inverse into A, so B is left free. This cannot be opened, so I will keep it as this. Is equals to any matrix, if you multiply with I, you are going to remain the same matrix. That means A inverse. That means if you multiply any matrix with I, you will be left with the same matrix. Okay. Now, see, look at this. A inverse into A. Can you see this one? A inverse into A. What it is? I. So this is I into B. Okay. Into AB the whole inverse. What is left here? A inverse. I already said any matrix, if you multiply with I, you will be getting the same matrix. Can you see this part? I into B. I into B. What is I into B? It is B itself, right? So this is B itself. A into B, the whole inverse is equals to A inverse. Now this is left. Again, pre-multiply with B inverse. Okay? Pre-multiply with B inverse. Pre-multiply with B inverse on both sides. Okay. B inverse. Okay, I just want to write this as it is so that I can show you what I'm doing. Okay. B into AB the whole inverse is equal to A inverse was the statement. I just wrote this statement as it is. Now I'm multiplying B inverse on both the sides. See, B inverse here and B inverse. This is what I did, right? Okay. B inverse into B. Somebody can tell me? A inverse into A is I. In that case, what is B inverse into B? Yes, you are right. It is I. So I into AB the whole inverse. This is equals to B inverse into, and any matrix multiplied with I will remain the same thing. That means see here, I multiplied with X is X only. So I multiplied with this will remain the same as it is. AB the whole inverse, which is equals to B inverse into. This is our proof. This is okay. Practice this theorem. So again and again. So you'll be very perfect in this theorem. Okay. So and after practicing, please write the theorem without seeing and try to verify your steps again and again. Okay. So thank you. Till then, be at home. Be practicing all the problems. So until we meet each other. Okay. Thank you very much.